Thank you and good morning. Today's presentation is going to be about what Azul have been doing in terms of helping to improve the performance of Java on the Raspberry Pi. As a company, what we're really focused on is trying to improve the performance of Java, and I'll talk about what we do and how we do that as we go through the presentation. Now, what I'd like to do is start with a poll. So I'd like to ask the audience, if you're developing embedded applications, how important is Java performance for your application? And I've given you three possible answers here. One is that this is critical to the project's success. One is we always want more, but we make do. And the third one is we have no performance issues. So fairly simple question. I'll give people a few seconds more to answer that. Then I will close the poll now, so if we can see the results. Yeah, there we go. Oh, okay, that's good. Okay, so most people say we always want more, but we make do. In fact, everybody says that. Okay, so that's good because that means that the audience are the right audience for this particular presentation. So we can discuss what it is we can do to improve the performance of Java. Now, to start with, let's talk a little bit about who Azul Systems are. We are a company who've been around for, well, like over 15 years now. We started off doing Java performance, but in hardware. And we actually made our own chips, and we created some systems called Vega, which had massively multi-parallel chips, which were designed to address the needs of garbage collection from a hardware level. Since that was quite an expensive process and quite a detailed process, we actually switched to a software solution about 2012. And so we now have a number of things that we do around improving Java performance on the commercial side, which is Zing. This is a high-performance, low-latency proprietary JVM. What I'm going to talk about today is our Zulu product line, which is certified 100% build of OpenJDK. And I'll explain all about how we do that, what that means, how you can use it, things like that as we go through. As I say, we're a small company, about 120 employees worldwide. We have offices in the US, we have offices in Russia and in India. As a company, we're also very heavily involved in Java. We're on the JCP Executive Committee. I actually represent Azul on the Java expert groups for Java SE 9, 10, and 11. And we even lead the OpenJDK 6 project so that we can backport fixes to that as well. So let's talk a little bit about the Raspberry Pi, because it's interesting to see how that came about and how we can then position Java as a platform for developing applications on that. And so if you look back in terms of the history of the Raspberry Pi, it actually goes back quite a long way. The project started way back in 2006, and the original goal of the project was to inspire children to get more involved in computer science. This was in the UK. I live in the UK as well, and I remember that at that time there was a lot of concern about children not learning real computer science. When they got taught ICT, as it's called here at school, what they were actually being taught was things like how to use PowerPoint, how to use spreadsheets and things like that, which is not computer science. It's how to use a computer, not how to program it. And the kind of inspiration that the people who started the Raspberry Pi project took was from another project that was done back in the 1980s. And again, I'm actually old enough to remember this because there was a thing called the BBC Micro. It was a computer that was created by the BBC, the British Broadcasting Corporation. And they did that so that they could produce a television program that would teach people how to program. And that was done in BASIC. And I was lucky enough to have one of these BBC computers when I was, I was about 16 when I had this. Great computer, absolutely fantastic. And I look back at that now and I think, how is it possible that you could do so much with only 32 kilobytes of RAM? That's it, 32 kilobytes, not 32 megabytes, not 32 gigabytes, 32 kilobytes. And yet some of the games, if you've ever seen things like Elite that used to be played on there, it's fantastic what you can do with these things. Anyway, that was the inspiration for the Raspberry Pi project. Now, in terms of how that moved forward, there was a lot of development work needed to be done. They came up with the ideas for what they wanted to do in terms of the hardware. They worked with the suppliers, and the actual first Raspberry Pi was launched on February the 29th in 2012. So it's coming up for 6 years now that this has been around. First production run was for 10,000 boards. Originally, the developers of this figured they probably only sell in the region of 20 to 30,000 boards total. And this was so successful at the launch of the product that both of the servers for the companies who were supplying the boards were completely stalled during the day of the launch. So this company called RS Farrell, and their servers literally couldn't deal with the load. I remember trying to order one myself, and I just couldn't get onto the server. And they reckon they had over 100,000 pre-orders in one day. Now, originally, the production of the Raspberry Pi was in China. That then moved to a Sony plant in the UK. And they're currently producing about 15,000 boards per day. So it's incredible to think how popular this board is. To date, they reckon that over 15 million have been sold. 10 million of those have been produced in the UK. And this makes it the third best-selling computer of all time, which again is a really fantastic thing when you think about this little board. It's third. The only two machines which have sold more are the Windows PC, or the IBM PC, I guess you could call it, and the Apple Mac. So those are the only things that sold more than this. So it's a really fantastically successful product in terms of where it originated from. Now, if we look at the different versions that we have available, most of them use the sort of familiar form factor, which is sort of slightly bigger than a credit card size. And there have been sort of a number of versions of this. So it started off with the Model A and the Model B. Model A was designed as a slightly smaller one, less power, less memory, and so on, and only had one USB port. Model B originally came out with 2 USB ports, and then it got upgraded, so it had 4 USB ports. One of the other really exciting things about the Raspberry Pi is the fact that it has these connectors that you can use in terms of GPIO, I2C, SPI, serial connections, which makes it really easy to connect devices, sensors, actuators, those types of things to the Raspberry Pi, and then control them from your application. More recently, we've seen the Raspberry Pi Zero, which is an even smaller version of the Raspberry Pi. It's probably about half the size of the actual original board. That doesn't have quite so much in terms of, it doesn't come with network connectivity by default. It has less connectors on it and so on. But again, it's incredible when you think that Raspberry Pi Zero in the basic form is only $5. How is it possible they can manufacture these things for $5 and yet give you so much computing power to do different things with and work on different projects? Now, if we go into a little bit more detail, I won't spend a lot of time on this, but this is really looking at how the hardware has developed over time. And it's quite interesting to see how we've increased the amount of memory, how we've increased the amount of processor speed and so on, which again is very useful when you're thinking about performance issues of your Raspberry Pi projects. So the original Model A was based on an ARMv6, only ran at 700 megahertz, single core processor. Early boards, 256 megabytes RAM, later ones, 512 megs of RAM, no Ethernet. Model Bs have evolved over time, so they've gone from the ARMv6 running at 700 megahertz, then moved on to an ARMv7 at 900 megahertz, then ARMv8, which gives you 64-bit processing capabilities, running at 900 megahertz, and now the latest one, the Model B3, runs at 1.2 gigahertz. So it's getting up to quite a reasonable performance level just from the point of view of the hardware. So quad core, 1.2 gigahertz, and the later versions have also got 1 gigabyte of RAM. Pi Zero, a little bit lower in terms of processing power because obviously it's cheaper. So ARMv6, but still clocked to 1 gigahertz and still has half a gigabyte of RAM. The Raspberry Pi W, which is the latest version of that, added Wi-Fi and also Bluetooth support built in. Now, because we're using the ARM processor here, that's a different platform, obviously, to what we're familiar with in terms of using the desktops and laptops that we have, which are typically Intel based. So I thought I'd just spend a moment talking about how the ARM process came about, because as you can see, I'm quite interested in the history of these things, and I think it's interesting to look at how this all sort of started off. So as I mentioned, the project that started off the whole Raspberry Pi thing was the idea of the BBC Micro. That was created by a company called Acorn, who were based in Cambridge in the UK. BBC Micro, as I said, had 32 megabytes of RAM and used a 6502 processor. Now, as I say, I learned to program on one of these devices, and it is a fantastic processor. I love the 6502. Nice, simple instruction set, lovely flat memory model, really easy to learn assembly program on the 6502. However, the idea that Acorn had once the BBC Micro became successful was they wanted to move into a bigger market, and so they wanted more of a business computer. When they looked at that, the 6502 they reckoned wasn't going to be powerful enough to run business applications. Very logical. So they looked around and they thought about how they could actually develop their own processor. So again, quite an undertaking was to actually say, right, we're going to develop our own processor. Not look around and find somebody else's, but we'll develop our own. And one of the areas they looked at was a project that was being run at Berkeley University in California. This was the reduced instruction set computer. The research that had been done at Berkeley showed that if you analyze the Unix kernel, which is the precursor to Linux, only about 30% of the instruction set on a popular 32-bit processor back in the day, the Motorola 68000, was actually being used. So although the processor had lots of esoteric instructions that you could use for different things, most of the time they weren't being used. So because this was sort of 30 years ago, the amount of transistors you could squeeze onto a single piece of silicon was quite small. And that meant that by adding more features in terms of instructions, you're reducing the amount of transistors you could dedicate to registers. Registers are how you make your computer faster because you've got faster access to data. So if you can increase the number of registers, you've got faster access to data and you can process things more quickly. So the idea behind the RISC project was to reduce the number of instructions, give back some space that could be used for registers, and then improve the speed that way. Again, interestingly enough, one of the processor architectures to come out of the RISC project was the Spark architecture that was the one that Sun came out with, and hence Sun came out with Java. From this came the Acorn RISC machine, ARM. That's the original meaning of ARM, Acorn RISC machine. 32-bit data, slightly bizarre, 26-bit address space, and 27 registers. And the first version of this was an Acorn Archimedes. And basically from that, a company spun off from Acorn, which became Advanced RISC Machines. And that's where ARM really came about. If we look at the features of the ARM processor, what you've got in its basic form is a 32-bit RISC architecture. The V8 now has 64-bit, but for the majority of the chips, it's a 32-bit RISC architecture. It's incredible to see that ARM accounts for pretty much 90%, I would say, of embedded 32-bit CPUs. If you look at iPhones, if you look at Android phones, if you look at tablets, pretty much all of these devices use a version of an ARM processor inside them. And I did some research, just updating my statistics to this last night, and the most recent information I could find was that there were 15 billion ARM chips sold in 2015, and that equates to more than 80 billion in total. And the most kind of impressive thing about that, if you like, is that not a single one of them were actually manufactured by ARM. ARM is purely an intellectual property company. It's the company that designs the processors. It provides the idea of the architecture, the core designs with the instruction set, but it doesn't actually manufacture them. So it licenses its technology to people like Apple, to people like Qualcomm, all of the big chip manufacturers that then create the chips based on that architecture. Last year or the year before, ARM were actually acquired by SoftBank, a Japanese company. So as I said, we get an abstract architecture, a microprocessor core design. The typical Raspberry Pi uses an ARM 11 architecture with an ARM v6 instruction set. Newer ones use v7, even v8, but if you're thinking about performance and you want to cover all of the Raspberry Pis, then you probably want to think of the lowest common denominator. Great thing about ARM processors, low power consumption, so they're good for mobile devices, good for IoT devices, things like that. If you look at the Raspberry Pi, you can power it off a 700 milliamp, 5 volt power supply. And the nice thing is you don't need a heatsink, you don't need a fan. So there's no extra equipment that you need in terms of actually making your processor work. Right, so we talked about the Raspberry Pi. Let's talk a bit about Zulu and OpenJDK. So this is the version of the JDK that Azul have created, designed to help you run your Java applications. So the first thing is, let's just talk a little bit about the OpenJDK itself. What is it? Well, the OpenJDK came about initially in 2006 when Sun Microsystems, who were at that time the custodians of Java, decided to open source their implementation of the JDK. Now, this was not a simple and straightforward process. There was a lot of due diligence that needed to be done, a lot of going through all of the files that were being used, making sure all the licensing was correct, and that Sun had the rights to open source everything. And so it wasn't until JDK 7 build 53 that it was a complete open source implementation. Up until then, there'd been a number of commercial closed source pieces that were still required. Things like fonts, things like color management, some odd things around sound and so on. But this is a big project. There are over 30,000 source files and over 7 million lines of code. So it's certainly a big project to use and to build. Now, the OpenJDK has had a lot of involvement, not just from Sun and more recently Oracle, who acquired Sun, several years ago now, back in 2010. So, as I say, lots of other companies are involved in this. IBM have heavily been involved in this. Azul, as I said, Red Hat have also made a lot of contributions. Even Apple, who decided that they were no longer going to support directly Java on the Mac desktop, then contributed the code that they had developed for their version of Java to the OpenJDK project, so that people could then build their own version of Java that would run on the Mac. Other people are involved. People like SAP do a lot of work on this, and even Twitter are involved in the OpenJDK project as well. In terms of how this relates to binary distributions, obviously most people, when they think about Java, they think about the binary distributions that come from Oracle, which we can call the hotspot binaries. IBM also have their own distribution. This is called J9. That was more recently open sourced. They open sourced the pieces that they had changed in terms of garbage collection and so on, and made that available. But they also have a binary distribution. Red Hat have a binary distribution that they make available called ICE-T, and as I said, Azul Systems have Zulu. There's a couple of other distributions which are not made publicly available, but are used internally. So both SAP and Twitter, although they work very heavily with the OpenJDK, they don't produce binaries that you can download. Now, in terms of what the Zulu OpenJDK is, it's a binary distribution of the OpenJDK. So what we do is we take all of the source code directly from the OpenJDK project and we run it through the standard build process. Once we've done that, we pass that all through the TCK tests. So there's the test compatibility kit, the Java compatibility kit, literally thousands of tests that need to be run in order to verify that the binary that's being produced complies to the standard that's defined through the JCP under the relevant expert group and JSR. Now, theoretically, we don't have to do that because the OpenJDK source code is in fact the reference implementation for the standard. So there should be no reason to do that. But to make sure that what we create is actually conform to the standard, then we run all the tests. We make sure that there are no licensing issues. So we've also written some tools that scan all of the source code files that we use and make sure that all of those have the right licensing associated with them, so there is no contamination of open source code with anything that's not, strictly speaking, open source code. This means that there are absolutely no licensing issues with using Zulu OpenJDK. It is completely free from our website. You can use it under a GPL version 2 with class path exception license, which means there are no field of use restrictions. You can use it wherever you like, for whatever you like, absolutely without constraint. So we verify absolutely built from 100% open source. In terms of support, when we're talking about the embedded side of things, we have versions for JDK 6, JDK 7, JDK 8, and JDK 9. Well, this is for the Zulu version. Currently, we're not supporting JDK 9 for the Raspberry Pi. The next release we support for the Raspberry Pi is going to be JDK 11. This is because with the switch to a long-term support release structure from Oracle, JDK 9 is not a long-term support release, so we've decided that we're going to match what Oracle are doing, and we will support JDK 11 in terms of Zulu embedded. If you want Zulu for the desktop, then you can get Zulu OpenJDK 9. It's also possible to customize Zulu embedded. So what we can do is, if you're interested in commercial use of Zulu embedded, then we can create specific packages for you. We can do that in a zip format, we can do it in the RPM format, we can do it in Debian format. We also have a number of bundles that we create for Java 8. So there's 6 builds of this in terms of either if you want something which is a headful, so it has a display connected to it. So you've got either the full JDK at 90 megabytes or the JRE without the compiler and so on at 72 megabytes. And then if you're looking at a headless implementation where size is really of the essence, then if you want the full JRE, that's 45 megabytes. And then we've got the compact profiles 1, 2, and 3, which goes from 14 megabytes, 18 megabytes, and 21 megabytes. So it is possible to shrink down the amount of code you actually need to a very, very small amount. Now, clearly with the Raspberry Pi, you've got 512 megabytes or a gigabyte of memory. So this is not so much of an issue. But if you're looking at targeting it to even smaller devices, then this could be something that would be useful. So how do you get started with Zulu OpenJDK? Well, what you do is you can go to our website and you can download the latest binary for free. So you don't need to pay us any money for that. You can just go there, download it. That comes as either a zip or a tarball. So you unpack that on your Raspberry Pi, put it in a particular directory, maybe the /opt directory, and then all you need to do is change your Java home and your path variables to point at where the Zulu binary was installed. That's it. That's all you need to do. Job done. It is a complete drop-in replacement for any other JDK. So if you've written a Java application and you're running it on a different JDK at the moment, and it's very, very simple to take the Zulu JDK and then run your application on that. So let's now talk about what we've done to help improve performance in terms of Java on the Raspberry Pi. And the specific area that we've looked at in terms of our work to date is around the C2 compiler. That's the JIT compiler. So first thing to understand is, how does the C2 compiler fit into what Java does? So we look at Java code that's generated by Java C. What we get is a set of bytecodes. This is a set of bytecodes that are using an instruction set from the Java virtual machine. This is where we get the whole write once, run anywhere, the ability to take our Java application that's been compiled into class files, move it from an IBM PC running Windows on an Intel processor, and then put it on our Raspberry Pi and not have to recompile it. So that's all good because we can develop on one machine, deploy on another. But what happens is that in order to make that work, when the bytecodes are loaded by the virtual machine, they have to be interpreted. So interpreted mode takes each bytecode and converts it from the virtual machine instruction set to whatever sequence of instructions are required for the specific machine on which it's running. In the case of a Raspberry Pi, it will be the ARM processor instruction set, the Linux operating system, so whatever system calls are needed. This is quite slow because every time you load a bytecode, it has to be converted. When you load the same bytecode, it still has to be converted. So it's not very efficient in terms of getting the best performance. To get around that problem, for a long time now, we've been using the idea of a hotspot just-in-time compilation. There are two different just-in-time compilers in the JVM, C1 and C2, sometimes referred to as client and server. What happens is, as you run your code, you will hit something like a loop, and the same set of instructions gets run many, many times. The JVM will spot that and say, oh, okay, rather than interpreting these bytecodes every time, let's compile that into native instruction sets and then have that run without having to interpret it. That can be done very quickly with the C1 compiler. So it compiles the code very quickly so that it can be made use of in an efficient way. But because it does it quickly, it doesn't apply any optimizations. This helps to improve the performance. And then once we've got slightly better performance through compiled code, we continue to profile that code to understand what's actually happening in terms of how the code is being used. As that set of instructions gets used more and more, it's then the job of the JVM to recompile that code using the C2 compiler. And the C2 compiler is an optimizing compiler, uses the profiling information that's been gathered whilst it's been running under the C1 compiled code, and then is able to apply optimizations in terms of speculative optimizations or better intrinsics. So we look at the typical sort of JVM performance in terms of how things work from a JIT compilation point of view. When you start running your application, what you're going to see is interpreted bytecodes. So from an overall performance perspective, that's going to be the lowest point of your performance. And the graph that I'm showing here, basically higher up is better. So this is speed. High is good, low is bad. So when you start off, you're running bytecode interpreting, and so it's slow. As the JVM monitors the application and identifies pieces of code that can be compiled, it will run the C1 compiler on them, and it will then enable the speed of that code to increase. But obviously it's not optimized, so you still won't get the best level of code performance. Then you get C2 JIT with the optimizations, because as the code is starting to warm up, there are these things called speculative optimizations that are applied, where the compiler will identify certain paths that you've taken so far through your code, and it will optimize based on that. But if you get situations where you suddenly don't take that path through the code, you may have to throw away the results of the compilation and recompile it again. So there'll be a sort of up and down learning process that occurs as the C2 JIT optimizes compilation. And then at some point, as your application runs for a certain amount of time, you'll get to a steady optimized state where you've got like the maximum level of performance. All of the pieces of code that can be compiled in a sensible way have been compiled and been optimized in the best possible way. So you'll get the optimal level of performance. But you'll see that, there is this warm-up curve that needs to take place, and that's what we're used to in terms of Java. In terms of what we've done to enhance the C2 compiler, we've tried to look at how we can improve things using the hardware that's available on the ARM processor on the Raspberry Pi. And one of the areas that we found that we could really take advantage of was the cryptographic side of things, because the ARM processor has a number of instructions that can be used to do this on the silicon rather than having to do it through software emulation. So what we've done is, wherever people are using cryptographic encryption, decryption, things like that, then rather than having to do it through the software in terms of what the JVM is doing, we hand it off to the processor and have it do it a lot faster there. We also found that there are some specific maths instructions that are available on the ARM CPUs that we can take advantage of to, again, improve performance in certain situations. And a third area that we looked at is that we found as we were doing this work, we found there were a number of sort of minor bugs, not so much in preventing code from running or making code run incorrectly, but from a point of view of performance, we were able to identify certain things whereby changing the way things worked, we actually got improvements in performance, which we classified as a bug in the code that we had. So we've improved performance that way. If we look at the results we get, this is using spec JVM. Obviously, you can use any set of benchmarks you like. For the majority of the benchmarks that we were looking at, our performance was pretty much the same as the hotspot JDK, but in the areas where we've looked at improving performance specifically, we can see quite a marked improvement in certain things. So as I said, for cryptographic things, in terms of the RSA test, we got nearly a 300% improvement in performance. For the signed verified test, we got 167. And then around some of the mathematics things like this, the Monte Carlo simulation, that was about 120%. Well, we actually, 120% improvement. And on some of the other ones, actually, that's not 100. That's not a percentage improvement. That's based on 100%. So it's to make it clear, the Monte Carlo was getting a 19% improvement. And the sparse small test was getting an 8% improvement. Derby was getting a 9% improvement. That's not 108% improvement over the other one. I should change the slide on that. So just to summarize, in terms of what we've been doing to make Zulu OpenJDK as good as possible for running your Raspberry Pi applications, what you get from Zulu OpenJDK is a certified build of OpenJDK source. It's free, available under a GPL v2 with class path exception license. As I said, we've worked on enhancements for the C2 compiler. We're looking at other areas where we can improve things even further around that. If you're interested in deploying this into a commercial type of environment and you're looking for support, then we have full 24/7/365 support available. Obviously, you can go to our website and find out more details about that. One thing to bear in mind is that as of JDK 9, Oracle will no longer be supporting any binaries for ARM processors. That was announced at the end of last year, just before Java 1, and Oracle have made the decision that they no longer want to create binaries for the ARM processor. So you can get binaries from other people. There are builds of the OpenJDK, but these ones where people are not doing the work that we've been doing in terms of improving performance around the compiler and so on. In terms of getting access to this, as I say, go to our website, download Zulu Embedded, and that's where you'll find the latest version that you want on our website. So with that, that's the end of the webinar. What I'm going to do now is throw this open and see if we have questions. Let's see. Right, okay, so question is, will the presentation be available for download? Yes, I will put the slides onto SlideShare, but we will also send all of the slides to all of the attendees, anybody who registered. There will be a recording of this made available as well, so if you want to watch it again or if you want to share it with your colleagues, then you can do that. So yes, it will be made available. So one other question is, what other ideas do you have for improvements in terms of performance? We're always looking at how we can improve performance in Java. I mean, obviously that's the whole reason our company exists, really. And so I think that there will be a lot more work around some of the compilation side of things. One thing I didn't mention is around the garbage collection side of things, because at the moment we don't support the G1 collector. The reason for that is that we found that we weren't actually getting very good performance from that. So in order to possibly improve performance, we may want to support that at some time in the future. One of the reasons we don't get such good performance out of G1 is typically used for bigger heaps. So of the order of sort of 10, 12 gigabytes gives you the best possible performance. So having only 512 or 1 gigabyte of RAM in total on the Raspberry Pi means that G1 is probably not best suited to that. So again, we might look at how we can improve performance around things like the concurrent mark sweep collector to optimize things specifically for devices and applications where you've got a smaller heap size. So with that, I don't see any more questions. So I am going to thank you very much and end the webinar.
Thank you, Simon, and thank you everyone for attending today's webinar. You will receive a follow-up email within 24 to 48 hours with the link to view a recording of today's webinar. On behalf of ASUS Systems and our presenter, thank you for joining us today and have a great rest of your day.